Okay, so today we're going to introduce some new connectives, but before that I want to just finish off one thing that I started talking about last time but didn't quite get through. I didn't get to show you an example of this, which is writing show lines, and specifically writing your own show line. So some problems will not be solvable unless you write your own show line. A couple things to note about show lines. There are no show lines that you ever have to justify. You never have to tell me what your reason for writing the show line is. Every other line you must justify. Every other line has to have some rule that you cite. How did you get this thing? Where did it come from? That's what we're doing here with the derivations. We are making arguments where every single tiny little step gets justified, except for the show lines. The show lines are the parts where you're just saying what you want, what your goal is. So you don't have to justify a show line. Furthermore, you can write a show line at any point in the proof. You can write any show line that you want. You won't always be able to show that thing, so you might sometimes get stuck, but you can start one unprompted. And this is often helpful for getting yourself unstuck. Once you've done the automatic moves, you've done everything obvious, you still don't know what you're going to do. Sometimes that's usually going to be the moment where you start looking around to decide, what show line should I write? So let me show you an example of this, of us getting quite stuck and then writing our own show line, getting us unstuck, mostly via doing an indirect derivation. Okay, so, good. So, pretty standard derivation. Let's get started on it. Line 1. We are going to show this conditional if S, then R. Okay. Now, anytime you want to show a conditional, except in very, very weird circumstances, you're going to want to start a conditional derivation. We introduced those last time. We introduced conditional derivations where we assume the antecedent, and I'm going to cite a justification for that. I'm going to assume for conditional derivation that the antecedent is true, and if I can show by assuming the antecedent that the consequent follows, then I've shown that the conditional is true, right? So far, so good. So now I want to write myself another show line, show R. Okay. Notice, again, I haven't written anything in this column for these two show lines, nothing. Because I don't have to justify my show lines. Yeah? I'm going to go through this by hand, and then I want to do the exact same derivation in Logic 2010 because it's Logic 2010. It takes some getting used to. So let's do that in just 1 minute. Okay. Okay. So anytime you're trying to show a conditional, you start a conditional derivation. For right now, anytime you're trying to show something that's not a conditional, you start an indirect derivation. So I want to say I'll give myself not R by saying assume for indirect derivation. Okay. So far, so good. I've written myself a couple show lines. These are just kind of automatic moves. These are moves that, if you got to show a conditional, you start a conditional derivation. You want to show something that's not a conditional, you start an indirect derivation. Okay. Now what? Ooh. There's nothing, right? We've only got one premise, and that premise is a big, huge conditional. It's a conditional made up of two smaller conditionals. And I have not got the antecedent or the consequent of that big conditional, right? So I can't do anything with it. And remember, you're not allowed to apply rules to just the parts of the conditional. You're only allowed to apply the rules to the major connective of the sentence, right? So I need the whole antecedent or the whole consequent to do anything in this derivation. So I'm kind of stuck. I did everything they told me to. I did all the automatic moves. Nonetheless, I'm stuck. The thing to do here is to write yourself a show line, right? Unprompted. So it's no longer an automatic move. I haven't been forced to, by my basic rules of derivation, like if I want to show this, I do assume CD. If I want to show this, I do assume ID. I'm going to write myself a new show line. In this case, what it would be nice to have is the antecedent of this premise 1. It would be nice to have that, so I'm going to try to show it. So I'm going to try to show if Q, then not S. And I don't cite anything. I don't tell you what my justification for that is. I just do it. I just say, I'm going to try to show this thing. OK. Now our old rules kick in again. The rules that we've already learned. I'm trying to show a conditional, so that means that I'm going to assume the antecedent, assume for CD, and now I'm going to try to show the consequent, not S. And not S, well, I'm going to assume, again, I'm trying to show something that's not a conditional, so assume ID. I could say not S, but let's just say not S. This is where our rule that you can give yourself the version that you want is helpful. I could have said not S, but let's not, shall we? OK. Now maybe we can do some stuff. We've got more resources now. By writing that show line, I opened up more resources for myself to work with. I've got more available lines. So let's take a survey. What lines have I got available? I've got line 2 available. I've got line 4 available. I've got line 6. I have line 8. Now I also have this premise 1 available, but as I said, so far it's not that useful to us. So far, we can't do much with it. If I've shown once I've shown line 5, once I've finished this subderivation, then I can do something with premise 1, but so far nothing. OK. So let's see. We've got S, not R, Q, and not S. Oh, hey, that's the opposite of line 2, right? And to close off and assume ID, one of the easy ways of doing that is to find a contradiction. So good. So what I'm going to say is line 2, repeat. I use the repeat rule to bring line 2 into this subderivation. Line 2, repeat. And line, I'll just write it for the sake of being complete. And now on line 8 and line 9, I have my indirect derivation. These two contradict, meaning I can cancel this show line and box this off. OK. Now, let's take a breath. Are you with me? Yeah, a question? So the question is, why did I do show not S rather than just saying line 2, repeat, double negation, and close off the conditional derivation? That's a fine way of doing it. There's nothing wrong with doing that. So what I said last time was, if you start a conditional derivation, this second show line, the show the consequent, is kind of optional. If you know you can get the consequent without doing this show line, that's fine. I always do this show line because it's always potentially helpful. It's always potentially helpful because I can always start an assume ID and it gives me one more thing to work with. It helps me remember what it is I was up to. So for a lot of practical reasons, I find that second show line to always be helpful, and it can never hurt you. So I always do it. It's not wrong if you don't do it, but I recommend it as a sort of strategy. Good question. OK. OK, so I've showed the consequent of this. So by assuming Q, I showed not S. Actually, I didn't use Q anywhere in that, but nonetheless, I showed not S, right? Which means that on line 7, I've done my conditional derivation. So I've shown the thing that I set out to show in this subderivation. Good. Now, what I've done for myself with that unprompted show line, it wasn't a show line that was forced on me by the derivation exactly. It's I decided that there was something that I wanted, something that would be useful to me, and that I thought maybe I could get, which is the antecedent of premise 1. So it's a good idea, it's very often going to be a good idea to try to show the antecedent of a conditional that you have or the negation of the consequent. The antecedent lets you use modus ponens, and the negation of the consequent lets you use modus tollens. So in this case, I did the antecedent. So I have if Q, then not S. And this premise 1 says if you have this, then you get this. So now I can say line 5, premise 1, modus ponens, and what I get is if not R, then not S. Great. So now I've got this thing. I was trying to show R. I assumed not R for indirect derivation, meaning I have not R available. Let's do another survey quickly. Let's do another survey of our available lines. S is still available. Line 4, not R, is still available. This is no longer available, and this is no longer available. Why are those no longer available lines? Because we boxed them. Those boxes, that's what these boxes say. These things are no longer available. This show line is also no longer available. It was available for a little while we were in this subderivation, but because this larger box is around it, none of these lines, so 6, 7, 8, 9, 10, 11, none of those are available lines anymore. But 5 is available. We used it to get 12. So we've got 2, 4, and 12 available. Since we've got 4 available, it's even inside our subderivation. We can say 4, 12, modus ponens. Not R is the antecedent of this thing, giving us not S. Okay, now we're almost done. Yeah?
You didn't have to write line 5 for line 12. You have to repeat it or anything?
No, we didn't have to repeat because it's in the subderivation that I'm currently in. You see what I mean?
Yeah.
So line 5 is now an available line, and what line 5, because I crossed out I didn't cross out the whole of line 5, I just crossed out the show line. Now line 5 has available for me if Q, then not S. So I can use it. Within this subderivation, I can just use it. Okay. Outside of this subderivation, I've got S. Down here, I've got not S. Right? This is still an available line. I have to bring it into my subderivation by saying to repeat. But once I've done that, to repeat, line 13, ID. So to, I brought it in here with the repeat rule, and these two together with 13, S and not S, are an indirect derivation. So now I cancel the most recent show line that I did, box and cancel, and I'm just about done. So now on line 3, I showed R on the basis of S. That means that I can say line 3, conditional derivation. Box and cancel. Ta-da. Okay, so the point of that example was to refresh us on the mechanics of doing derivations, but mostly it was line 5. Line 5 was the important one there, because line 5 was where I said I got to a point where, look, I'm just stuck. I'm stuck. I don't know what to do. I don't have a lot of options. I don't have a lot of moves I can make with what I have available. By writing a show line for myself, I was able to start a conditional derivation. Conditional derivation gives us some moves we can make. Similarly, I could have started an indirect derivation. If it wasn't a conditional that I was doing a show line for, I could have started an indirect derivation. And that indirect derivation opens up resources for me to work with, right? So the game here is really trying to get yourself resources that you can do things with. And it's almost never a bad, it's typically not a bad move to do whatever you can that opens up resources for yourself, right? There's no points for writing the shortest derivation on the test. If you make a move and open up a resource and never use it, that's kind of fine, right? Once you're a famous logician and you're publishing papers in logic, then you can worry about having derivations that are pointlessly long. Currently, that's not a problem at all, okay? Okay, Yeah, yeah. And indirect. So the question is, how did I know to start a conditional derivation? You mean on line 5? Yeah, so I knew to start a conditional derivation because the thing that I wrote a show line for is itself a conditional. Right? So if Q then not S, that's a conditional. The major connective of that sentence is a conditional. So again, basically any time that you write a show line, even if it's a show line that you're coming up with yourself for a conditional, it's a good idea to start a conditional derivation. Again, I hedge this a little bit because there are some weird circumstances in which you're not going to start a conditional derivation, but those are really weird circumstances. And you can always get by doing this, so you might as well at this point in your logic career just think, if I'm trying to show a conditional, start a conditional derivation. It's a good rule for you right now. Okay. Any other questions about this? Yeah. Sorry, I didn't quite hear you. Yeah. Sorry. On line 2, I wrote show R, and on line 13, I did what? I literally just can't hear you. On line 13, I'm doing a modus ponens. On line 14, you mean? Yeah, right, so on line 3, I don't have R yet. I showed R on the basis of line 14. Right, so line 14 is where I got R. It's not where I. You see what I mean? Oh no, okay. Okay. Maybe it will help if we go through this. I want to go through this same derivation one more time, but this time in Logic 2010, if that's okay. Let's try it and see if that clears it up. And if it doesn't, maybe talk to me after. If you're still confused, talk to me after. We'll sort it out. Okay. So this is partly by way of exploring this derivation a little more, partly by way of going over the controls for Logic 2010 again, and a few more details of the controls. Okay, so I'm going to say show conclusion, and that generates a show line for me. Okay, I didn't need to do that, and show conclusion is not a justification in our system. So I could have said the following. I could go over, so instead of I press tab and that switches me between these two columns. Instead of writing show conclusion there, I could have said show S conditional R. And the key control for conditional is Control-Shift-C. And it does that for me. Yeah? And I'm going to say assume for conditional derivation and show consequent. Again, show consequent is not a justification. It's not something that you should write in your proofs, because I could have easily said show R, and that would have been exactly as good. Okay? I'm going to assume ID, and now we're back where we were. Okay. So now it's time to write my own show line. Yeah? Okay. So again, there's two different ways to generate the show line. It's perfectly fine to go show if Q, then not S. Yeah? Here's another way of doing it. You can say show antecedent premise 1. But that, again, is not a command it's not a rule in our system, show antecedent premise 1. It's a thing that you can type into Logic 2010 to get it to generate the show line for you. That seems like maybe it's not that much work right now, but as we progress into the course, the formulas you're going to be dealing with are longer and longer and more complicated, and they become more tedious to type them out. So these controls are useful for generating the show lines that you want. We could have done, so there's a few of them here, and you can, on a Windows machine, you right click and you can show, so these are different show lines you could generate. So show negated consequent of premise 1. Okay. So we can do this, we can actually, so one question that you might have, that you should have, is how do I know what show line to write? How did I know to write the show line for the antecedent of the conditional rather than the negation of the consequent? And the answer is kind of just, well, you figure it out from the circumstances. And often you can do one or the other. So let's try this. Let's try doing the, last time I did the antecedent, let's try doing the negation of the consequent, yeah? So assume ID, if not R, then S, 4, repeat, 6 modus ponens, you get not S, 2, repeat, 7 ID, closes that off. So now I've got the negation of the antecedent. So I can say 5, now I can use line 5, premise 1, modus tollens to give me this. This would be useful to us if we had some of the more advanced rules in this course. So you can, there's a rule called negation of conditional that this would be helpful for. Actually, to finish this off, I have to write another show line. I have to say show, I have to write the same show line basically. It's not hard to do, but so this time I'll do 2, repeat, double negation, direct derivation. Great. So now I can say line 9, line 10, indirect derivation. Okay. Okay, so it worked out. I wrote a show line for the other thing, and it worked out okay. It worked out okay because I tried to generate a contradiction from what I had. 3 conditional derivation. And we're done. Okay. So this was just to show you some of the commands on Logic 2010. I'm sorry, I went really fast there. I take it that I did it slowly once by hand, and that was okay, and I'll do it quickly on Logic 2010. Notice how much faster and easier that was on Logic 2010. So much faster, so much easier, which is a deadly, deadly trap for you. I'm very serious. So it's almost time. It's not quite time yet, but it is very close to being time for you to start practicing not on Logic 2010. Because what Logic 2010 does for you is, you can see, I type in a command and it fills out the output for me. So Logic 2010 is doing half the work for me. It's checking for me whether I did it right. So if I type in something wrong, it'll give me an error message. So it's doing like more than half of the work for me. So here's what a bunch of you are going to, despite me giving you this warning, here's what a bunch of you are going to do. You're going to do all your practice for test 1 on Logic 2010. You're going to sit down in the test, and you're going to go, oh my God, I forgot how to do logic. That's what's going to happen to you. I guarantee that's going to happen to a bunch of you. Here's how to make it not you that happens to. Practice pencil and paper. Okay? What I'm going to do is put up blank derivation sheets on Quarkus. I haven't done this yet. I'll do this tonight. Blank derivation sheets on Quarkus that look exactly like the sheets you'll see on the test. What I want you to do is print a bunch of those out and do your practice, pencil and paper, on those sheets so that you get very used to exactly what you're going to see on the test, doing it in exactly the context you're going to do it on the test. Okay? Do not fall into the trap of doing everything on Logic 2010 and then forgetting how to do logic, because you will not be able to make the transfer from one to the other seamlessly, because this is doing half the work for you. You'd be like, why is this so much more work than on Logic 2010? It's because it's doing half the work for you. So Logic 2010 is a beautiful tool. It's a wonderful tool to help you learn the skills. It's a very bad, like, If it's your only practice, it is very bad preparation for the test. Okay? Yeah, yeah. Oh, it's Control-Shift-C. Okay, I will also post on Quarkus a list of keyboard controls. There's keyboard controls in the FAQs for Logic 2010, but I'll make it accessible to you. Control-Shift-C is make it conditional. Yeah?
Are the little text things embedded in the software as well, like show neg cons premise 1? Is there a shortcut you can see all of those options?
Well, you could type it, and you can press right-click or control-click on an available line, and that gives you those options. Does that make sense? So I did do this on the, so right-click, show neg cons, and then just write in premise 1. Yeah? Okay, good. Okay, I got to move on because we got some new stuff to do, and I've spent all of the time, I think, on this that I can. Okay. So, writing show lines. Okay. So, the remainder of the stuff we have to cover today, I hope, is fairly intuitive. It's fairly, will make sense to you because you know how to speak and do basic reasoning. But nonetheless, we have to introduce it. So, here are some new connectives. We started off making this as simple as possible for ourselves by just dealing with negation and conditional. Now we got some new connectives. And, or, if, and only if. These are the last connectives we'll do for the course, by the way. There's some other fancier stuff that happens in predicate logic, but so far these are going to be all the predicates, or all the connectives we've got. So, here's some truth tables. Remember the truth table for the conditional, which was weird? Let me show you some truth tables that make sense. Conjunction, and. So, P and Q is true if P is true and Q is true. Got it? This is easy, right? This should be the most intuitive, straightforward thing in the course. P and Q is true. You can tell that it's intuitive because I have no other words to express this other than the logic. P and Q are true if P is true and Q is true, and false in any other case. Okay. Disjunction. Mildly trickier. It is mildly trickier because there's a couple different things. This is the disjunction is what we mean by or, but or could actually, in English, or could mean a couple different things, and this is the one that we're going to use for the rest of the course. So or is true, P or Q is true for our purposes. If P is true, or Q is true, or P and Q are true. This is what's called the inclusive disjunction. The inclusive disjunction. Okay. And biconditional. So biconditional is like a conditional that goes in both directions. The biconditional is true. So P biconditional Q is true if both P and Q are true, or they're both false. But if they have different truth values, then it comes out as false. This one's much less intuitive, but hopefully we do a bunch of examples and it will become more intuitive. And this is equivalent, by the way, to if P then Q and if Q then P. So the truth table for that comes out as the same as this. Okay. So in official notation, all these sentences get brackets around them. So our official, informal, not well-formed thing gets a little more complicated when we introduce more connectives. In official notation, these all get brackets around them. A convention. Let me introduce a convention now. This is something that I'm just saying, and there's no deep reason why it's this way rather than the other way. It's just, this is how the textbook says we'll do it. This is how Logic 2010 works. So this is how we're going to do it. So we're going to assume, if you've got if P, then Q or R, we're going to assume that the conditional is the major connective. For the rest of this course, we're going to adopt a stance of blatant favoritism towards conditionals and biconditionals. If you've got a conditional and anything else, a conditional or a biconditional and anything else, then the conditional gets to be the major connective. Right? So the brackets, this tells you, the brackets tell you that the or statement there is not the major connective. P, if P, then this thing. Okay? Okay. And the order doesn't matter. So if the or part comes first, P or Q then R, it's still the major, the conditional is still the major connective. Okay, this is just a convention. This is to make it a little easier to do informal notation. So if you give, this is the top thing is an okay sentence. It's a well-formed sentence in informal notation. The top thing is fine, and we're always going to read it as the bottom thing. Okay? Okay. Same thing with and. It's not exclusive to or. And is the same thing. Yeah? And the same thing with biconditionals. So again, we're having blatant favoritism towards conditionals and biconditionals. If there's a biconditional in the sentence and it's not clear whether that's the major connective or an and or an or is the major connective, we always default to assuming the biconditional is the major connective. Yeah?
Is there any informal notation for the and ors? Like if you combine them, does one take precedence for brackets?
We'll get to that in just 1 minute. Okay. So, in general, here's the rule. If there's a biconditional and a conditional, you assume it's the major connective unless the brackets tell you otherwise. So you can use brackets to make something other than the conditional or biconditional the major connective. So in this sentence, the major connective is the or. We've used the brackets to make the biconditional a part of the sentence rather than the major thing in the sentence. Yeah? So absent brackets, you default to the conditional or biconditional being the major connective, but you can use brackets to indicate that something else is. Okay. And I went over in some detail. Do you recall I went over this thing where if P then Q then R is not well formed because we don't know what the major connective is? Same thing if you're mixing conditionals and biconditionals. We don't have any preference between conditionals and biconditionals, so we don't default one way or the other. If you get P biconditional Q then R, that's not well formed. That's just we need brackets there to disambiguate. Okay? Okay. Now, if you have two disjunctions in a row, that's okay. If we say P or Q or R, that's fine. We'll assume that it's this thing, but you could have assumed the opposite. You could have assumed that the other or was the major connective. And it's fine because the truth values of those come out the same. Same thing with ands. P and Q and R, that whole thing is true if P is true and Q is true and R is true and false in any other scenario. If any three of those fail to be true, the whole thing comes out as false. And it doesn't matter where you put the brackets, that's still going to be true. So what we preserve here, the thing that we're concerned about, the thing we should worry about, is having unique assignments of truth to the whole sentence based on an assignment to the parts. Right? So these are truth functional, which says we have inputs that are truth values to the atomics, and that should give us exactly one output, which is truth values for the whole sentence. And if it's a string of ands or a string of ors, that truth functional property is preserved. You get a unique truth value for the overall sentence, given any assignment of truth values to the parts. Here's where it does matter. If you have a mix of ands and ors, if you're mixing ands and ors, now where the brackets go makes a big difference. Now you have to be specific. So the thing on the left there says it's true if P and Q are true or R is true. So either both P and Q have to be true or R has to be true. The thing on the right is true if P is true and either Q or R is true. And those are true under different circumstances. Okay. So two different ways of parsing this sentence, just to show you, just to demonstrate again why this is a problem. Because we don't get a unique mapping. Suppose we assign these truth values. P is false, Q is false, and R is true. That makes Q or R true. On the left-hand side, it makes Q or R true. But just one half of a conjunction, if you have an and statement, just having half of it true is not enough to make the whole thing true. Both halves have to be true. So we get a false one half and a true the other half. The whole thing comes out as false. Yeah?
If the truth values, let's say they both came out the same, what would you say? Would you say it's still not well formed?
It's still not well, so there are truth value assignments on which they do come out the same, but it's that to be well formed, it has to be under any truth value assignment. You get a unique mapping from inputs to outputs. So if there exists a truth value assignment that comes up with different answers, then it's not well formed. Good. Okay, and you can see on the right, P and Q, both of those being false makes the conjunction false, but just R being true is enough to make the whole sentence true, because the or statement is true anytime one half or the other is true. If you're looking to remember which one's and which one's or, imagine it's a person. With or is kind of the permissive one. It's like, whichever one is true. If one of these is true, that's fine. And is much more definitive. It's like slamming the fist down. It's like, no, they both have to be true. Or is okay. And is okay? Okay, so that's how you're going to remember which one is and which one is or. Okay. Okay, so let's talk about symbolizing these a little bit. So just like with conditional and negation, we've got a bunch of what are called stylistic variants. These are different ways of saying what add up to the same thing. Now, with and, these stylistic variants, you might not think are equivalent. So X and Y, sure, that's equivalent to and, that's fine. X but Y, that's the same, logically speaking, as and. X although Y, X even though Y, even though X, Y, despite X, Y. Now, as sensitive, intelligent, context-sensitive people, you can tell the difference between and but, right? Jane's going to be at the party, and I'm happy. Jane's going to be at the party, but I'm happy. Despite Jane being at the party, I'm happy. Those are very different sentences, right? But they're different in a way that doesn't matter to the truth values of the sentence. So if I say Jane's going to be at the party, but I'm happy, it's true that Jane's going to be at the party, and it's true that I'm happy. Right? Those things both have to be true for that sentence to be true. They differ in their connotations, but recall that we're not dealing with connotations in this class. We're just saying truth values. That's all we care about. So this is sort of counterintuitive, but anytime you see X but Y, you're going to say that's a conjunction. It's an and statement between X and Y. Okay? We will practice lots of these. Okay, so these are stylistic variants. If you see a sentence with any of these in them, then it's an and sentence. Okay, here's another one, not both. We symbolize not both as the negation of a conjunction. So not both Peter and Quincy came to work today. It's not the case that it's true that both of them came. It's false that both Peter and Quincy came. So it's true if either of them didn't come, right? So the not and is it's false that this conjunction is true. The conjunction is true only in case both of them are true. So it's false if either of them are false, not both. Yeah? Okay. Some of these are straightforward. So here are some stylistic variants for or, x or y. Either x or y. Here's one that's confusing. X unless y. What? So this again is a case where logic doesn't capture everything that you might think is important about language. I'll be hungry unless I eat lunch. That's true if you're hungry or if you eat lunch. What we're going to say, and I'm basically going to stipulate, in the case where you eat lunch and are hungry, the sentence is still true. That should bother you a little. It doesn't make perfect sense. So it's our logical system, a couple times during this lecture, our logical system has not fit natural language perfectly. There's a kind of imperfect fit between the logic and between how you understand sentences in a normal context. But nonetheless, and this is how we're going to do it. So if you see unless, we're going to assume it means or. Unless has a flavor of what's called the exclusive disjunction, right? So if I say either I eat lunch or I'm hungry, it sounds like what I'm saying is one of these things is true, but not both of them are true. That's the thing on the right, the exclusive disjunction. So it's false if both are true. It's true if either one of them is true, but it's false if both of them are false. So that's a reasonable reading of the word or. Perfectly sensible reading. It exists in lots of logical systems. But for the whole course, for the rest of the course, we're only going to use the inclusive or. Okay? We're only going to use inclusive or. Or is always going to mean it's true if they're both true or if one of them is true. Unless I think it fits a little better with the exclusive or. But nonetheless, if you see an unless in a symbolization problem, it will be represented as or. Okay? Yeah?
So, is an unless as well like a negation of the consequent and the implication of that?
I'm sorry, the negation of the consequent, we're not dealing with a conditional, so there's no consequent. Okay, so there are some equivalences between a conditional and a disjunction, but let's leave that for now because I'm running out of time and I gotta. I'm sorry. There are equivalents. So if you're seeing an equivalence here between the negation of a disjunction and a negated conditional, then or negated consequent of conditional, then you're onto something. I just don't have time to get into it right now. Sorry. Yeah. Okay. And neither nor. So if you say neither this nor that, the negation of a disjunction. And by a rule that we'll learn later called De Morgan's, this is logically equivalent to not x and not y. But it's enough for you to know right now that this is just, those two are two equally good ways of representing the same thought, neither nor. Okay. And finally, stylistic variants for if and only if. X if and only if y. People don't normally talk this way, but x exactly on the condition that y, x just in case y, and x is necessary and sufficient for y. All stylistic variants for the biconditional. Okay. So because these are so unlike the way people actually talk, I kind of recommend just memorizing these. Be sensitized to them as indicating the biconditional. Okay. Really, really quick, I'll do one or two examples. Okay. So, Veronica will leave if and only if William won't leave. It's a biconditional, right? There's some kind of the if and only if tells us that this is a biconditional. Veronica won't leave, so not V. Veronica won't leave, not V. If and only if William won't leave, not W. I'm sorry, we got 2 minutes left, so I'm gonna have to really zoom through these. If you have questions about them, maybe bring them to the Quarkus. Okay. William and Veronica will both leave if Yolanda does, provided that Veronica doesn't. Ugh, okay. Once again, the comma is really important. The comma indicates a break in the sentence. So provided that, and often it's helpful to rephrase things. So provided that is like if. So if Veronica doesn't, so not V. And whatever comes after if is the antecedent, right? So if not V, then this whole thing. William and Veronica will both leave if Yolanda does. Once again, whatever comes right after if is the antecedent, so Y, then William and Veronica will both leave. So W and V. There you go. We could have put an extra pair of brackets in here to just indicate that this is it, but our blatant conditional favoritism means that we didn't need to. Okay. That's all the time we have. Thanks for sticking in.